So here today, we're going to talk about modern applications. So what does that even mean? This work grew out of a deck we built by our analyst relations group, and the analyst kept telling us that you guys have 140 services and no opinions. And so, I don't think it's appropriate for Andy to get up on stage and tell people what to use, but what is appropriate is we can look around and see what our successful customers are doing, and also what the teams internal to AWS are doing, and learn from that and hopefully pass on some of these messages here. So we built a deck for the analyst, and I was the technical consultant on that. And it came out well enough that we've been taking the message here to AWA to reInvent to talk about it. There's been several other presentations on the subject, mostly focusing on the issues of what the business advantages of modern applications are and what you can hope to achieve by doing that. But I'm not going to do that very much. I'm going to talk mostly about the how, and I'm going to illustrate it by ripping the covers off and diving into the internals of a few AWS services. So the other presentations are over, so we can skip past that slide. And we can skip past this slide too, and talk about traditional applications. Since we're talking about modern applications, I'm an old guy. I've seen a lot of traditional applications. And what we have here is a traditional application, a successful, happy AWS customer that's in the business of teaching children to write, good penetration in the early childhood education market. And what I have here is the architecture of their application. Isn't that just the greatest, simplest thing imaginable? They got a load balancer, they got a web framework, and they got a database. Is this bad? No, this is great. It's simple, it's straightforward, it's easy to understand. And it's got a subtle advantage, which is that there is no mystery whatsoever as to where it is that application state might be living. The application state is what the database says it is. And that means that if the worst thing imaginable happens, and your database melts down and your host melts down, well, assuming you've been moderately careful with your journals and snapshots and so on, you can recover your state and get back on the road. So that's good. So the question I have is, should you build applications like that? And the answer is, yeah, you absolutely should, where you can. Now, inside AWS, the number of occasions where we can build applications like that rounds to zero. Simply because everything we do has to be able to scale to huge fleets to handle tens of thousands or hundreds of thousands or millions of transactions per second. We have to deploy all the time in many, many regions, and we have to build it at a price level that's low enough that we can sell it to you at a price level that's lower than you could get yourself and still make money. But nothing wrong with traditional applications. So for modern applications, here is the list of principles we put in the analyst deck of what the guiding tenets are for modern applications. Now, I'm not going to dive into all of these at equal depth. To start with, for example, on the security front, you get a lot of the benefits just from being in the cloud. Just by being in the cloud, you get web application firewall and GuardDuty and Sentry and CloudTrail and config and all those things. And you also get to hire our security group, which is much bigger and more expert than you could possibly hire yourselves in most cases. So in fact, I'm only going to spend my time mostly on items number 2 and 3 in this list, and then add a couple of other items that I think are super important for modern applications. One being databases, because we got database news here at this conference, and then talk a whole bunch about integration, because nobody builds stuff in the cloud. So let us dive in and talk about, what do we talk? We'll talk about microservices first. Now I got to ask myself, in 2018, do I actually still need to explain why microservices are a good idea? I don't think I need to spend a lot of time on it, but I think I won't be wasting either your time or mine if I put one slide into it. So let's talk about why microservices are great, and let's do it by ripping off the covers of AWS's simple queuing service application and looking how it works inside. Now, there's a bit of irony here, which is that this is one of our very oldest AWS services. It debuted in 2006, 12 years ago, and the word microservice never actually appeared on the internet until 2011, near as I can tell. But nonetheless, it's still microservice-based if you look inside. In fact, there are 4 distinct microservices I'm going to talk about. There's the front end, which talks HTTPS to the world, and nothing it does, I think, would surprise anybody in the slightest. Then there's the back-end service, and the way it works is it deploys the messages, it actually stores the messages that are in flight on the queues, and it does so on a large number of clusters. Each cluster is a small number of hosts in multiple AZs, and as is usual with AWS services, we do not acknowledge receipt of the message until it's hit the iron on 3 AZs. Then there is a metadata service backed by Dynamo, and its only role in life is to know which queues are on which clusters. It turns out a queue can be on multiple clusters, and it can move around between clusters, which is why SQS can scale to effectively infinite throughput. But it's also the reason that SQS cannot guarantee deduplication or perfect in-order delivery. Finally, there's a load manager service that runs around and looks at all the clusters and detects if any of them are getting hot or are underutilized and moves queues around and splits queues where necessary. There's an interesting definitional problem here. Some people get all religious and say something's not a service unless it's got an HTTP endpoint and accepts requests. Well, that's just not true, because this is a server by any meaningful use of the word, and it doesn't accept any requests. It just proactively runs around and takes care of the back end. So why are microservices brilliant? Well, this has been running since 2006, and do you think it's the same code now it was running in 2006? Not in the slightest. The benefit of a microservice is that it's something that can be scaled and deployed and refactored and improved incrementally without disturbing the rest of the picture, which is what we do all the time. To name one big example, that database there used to be an Oracle database at one point in the history, but we turned that off and moved it to AWS DynamoDB. Can I say that again? We turned the Oracle database off. I want to say that again. We turned the Oracle database off and moved it over to DynamoDB. It makes me so happy to say that. Now here's another real triumph of microservices. Earlier this year, we decided that we were probably wasting some resources on our back-end fleet because those things didn't seem to be running very hot. And so we thought about trying to do a refactoring to make it run more successfully. And I hope we can get those guys to come here next year and tell the story, because it's a hell of a story. They succeeded brilliantly. They had to reorganize the way the database works, but they got a several-fold improvement in throughput per host back there, which ended up in saving us a big enough amount of money that it's even noticeable at the Amazon scale, which is really a lot of money. And also, it reduced the size of the back-end fleet dramatically, making it much, much easier to manage and take care of. Now, if you're smart, you're thinking, oh, well, okay, it's reasonably straightforward to rev the software in a microservice, but this is a database migration because they changed the database. And database migrations are a pain in the butt. But this is not just a microservice. It's sort of a microservice because the software running in each cluster only knows about the other hosts in that cluster. It doesn't know anything about the larger picture. And so what we could do is we could roll in new clusters running the new software, and then eventually, as the messages aged out, take the old clusters out of service, and then incrementally move from old database to new database without anybody ever noticing. You couldn't possibly do that if you weren't in a microservice architecture. So microservices are really just the way to go. It's the conventional wisdom. It's the conventional wisdom for a good reason. And if you are building anything substantial and distributed that needs to scale, and you're not using microservices, the balance of evidence would suggest that you are wrong. So that's all I'm going to say about microservices. Now, if you look at that picture, is there any way in which that application is manifestly not modern? Well, sure. With the exception of DynamoDB, nothing on there is serverless. So I think that perhaps the most important piece of advice in our modern applications deck is that you should try and be serverless where possible. Why should you try and be serverless? Well, these are the obvious main headline reasons. You might save a really lot of money, particularly if you have a load, and the idea of serverless is you're not paying while it's not running. The cost savings that we're seeing from real customers are just enormous. Secondly, security. Anytime you are running something serverless, you can't see the host, which means we have to take care of them, which means we can bounce them and so on whenever we need to patch the OS or fix something or they crash. And the effect is that the incidence of old, unpatched, out-of-date hosts running in serverless applications is very low, vanishingly small. So you get a noticeable security delta by going to serverless. The third one, of course, is elasticity. We scale for you. Capacity planning sucks. It's a really unpleasant, difficult activity, easy to get wrong. And the penalty for getting wrong on the high side is that you are throwing away money. The penalty for getting wrong on the low side is that you are inflicting pain on your customers. So just don't do that. Go serverless wherever you can. So those are the big reasons. Now, take a moment and think and realize those are all pure business reasons. I haven't said a word about technology yet. Is there anybody in the crowd here with a suit? Oh, come on, biz casual, polo shirt, pantsuit? Well, sorry, but if you were there, this would have been for you. So let's talk about the technology. When you go serverless, are you also going to get a better design? Maybe. I don't actually know. I'm a functional programming geek. I really like the feeling of dealing with stateless functions in the cloud and services where I don't have to provision and they just scale along with me. It feels right. It feels good. It feels modern. But do we have enough evidence that I can stand here officially and say, yeah, you'll get a better design with serverless? But you know what? I'm pretty sure you're not going to get a worse design. And frugality, security, elasticity, go ahead and do it anyhow because it's the right thing to do for purely business reasons. Having said all that, I'm now going to make an argument that you will get a better design, and here's why. So here's a snap from Werner's keynote last year. Disclosure, that was my soundbite. I lobbied to get it into the speech. And that's sort of the end game. That's the goal we're all aiming for, that we all want to get to, so all the code you ever write goes straight into something that is measurable business value add. You're not writing code to configure Kubernetes. You're not writing code to deploy IAMs. You're not writing code to manage autoscaling. You're not writing code to do all those other things. So think about it. You have a finite amount of time to design your application. So if you're spending all that time thinking about the design of your business value add code, you're going to get a better design, simply because in a serverless context, you have more time to put into it, just because you're not doing all that other stuff. So I think it's very reasonable to believe that you probably are going to end up on software quality when you go to serverless. So, should we all drop everything and write everything in serverless from here on forward? No, not necessarily. Our advice specifically is use serverless where possible. So what does where possible mean? Well, let's use an example. And the example we're going to use is Amazon MQ, which is a service that we launched at this event last year and is doing very, very well. It's basically a managed version of the Apache ActiveMQ message broker. And so basically half of the service is just MQ, and the other half is the control plane, the software that we use that you can call RESTful APIs to create brokers, delete brokers, start brokers, stop brokers, all that stuff. The control plane is 100% serverless. Lambda, API gateway, Dynamo. And that's as it should be. I think that we have convinced ourselves that for that kind of thing, any design that is not serverless is probably just wrong. I mean, what sense does it make to have a host sitting there turning electricity into heat, waiting for somebody to decide they need to make a new message broker? It doesn't happen that often. It takes a long time to create a new message broker, sometimes minutes. It's just obviously the right thing to do serverlessly, and we do. And I think that if you tried to do something like this in a non-serverless way, I would question that. Now let's talk about the other side of the equation, ActiveMQ itself. ActiveMQ is not a RESTful thing at all. It's a great big glob of Java code that and the clients open up permanent nailed-up TCP IP connections to the message broker, and when they want to send and receive messages, they just send bytes up and down the wire with framing protocols such as AMQP and STOMP and MQTT and JMS OpenWire, okay? This works fine. You can get remarkably low latency because you're not doing setup and tear down of HTTP connections. The bytes just come into the network into a Java buffer, and you look at the header and decide where they're going to go and send them out again. So you can get remarkably flaming fast low latency. On the other hand, since it's not serverless, you cannot expand beyond the bounds of the single instance of the broker that happens to have the nailed-up TCP IP connections. So is this wrong? Should this be serverless? I don't think so. I think this is perfectly okay. It's a perfectly decent piece of design. I can imagine a future in which we'll be able to somehow have a serverless architecture that still manages to do nailed-up TCP IP connections. And when we get there, that'll be fine. But at the moment, we're not there, and this is just fine. So here you have a very practical, concrete example of what I think we mean when we say serverless where possible. And of course, this is not the only service that's doing this. There are a lot of AWS services now that have serverless control planes. You're using some combination of API gateway, Lambda, Dynamo, and so on and so forth. I didn't actually go and do an exhaustive search across all the services, but there are some examples. But I left some space on the slide because I wanted to highlight one particular service with a serverless API gateway-based control plane, which is API Gateway, which is cool. So the service that you use to build your serverless microservice-based applications is itself a serverless-based serverless microservice-based service. Boy, that's hard to say, but it's a good sign. At the end of the day, we would hope to be able to build AWS on AWS, and this is a step in that direction. So we want to use serverless where we can. So I offer you one scenario where you might not be able to. Let's look at another scenario. People say, well, I'm nervous about going to serverless because latency. Serverless might have latency. And yeah, there might be issues around serverless and latency. So let's talk about that and see how big of a problem we think it really is and what we might do about it. So if you talk about latency, I hear an anti-pattern sometimes. People come to me and say, for this application I'm building, my latency threshold is 110 milliseconds. If you can't do 110 milliseconds, I can't talk to you. And my mind goes blank, because if you tried to have that conversation inside AWS, it wouldn't work, because we never, ever, ever talk about latency without talking about these P numbers. Now, most of you are probably familiar with them, but P50 means a time such that 50% of half the transactions complete in less time than that. P90 is such that 90% of the transactions, P99 and so on. Sometimes you'll even hear people talk about P99.9, and then there's P100. So in this particular example we're looking at on the screen here, if you can read those little teeny numbers, you can see that half the transactions completed in about a quarter of a second, 90% of them in a second or so, 99% of them in 4.5 or so seconds, and there were a few outliers up there in the 20-second range. And when you're thinking about your latency needs, you need to think about this. Is it okay if it averages around 100 milliseconds, but sometimes it spikes to 1 second? Is it okay if it sometimes spikes to 2 seconds? What percentage of time is it okay for it to spike to that? For those of you who are curious, this is actually a graph off one of the autoscaling services. And the reason, for EC2 autoscaling in particular, and the reason it's like that is most autoscaling groups have like 4 instances or 8 instances, but some have 25,000. That's why you see that pattern. So if you're going to talk about autoscaling, talk about latency, that's what you have to talk about. Basically, latency is more complicated than you think, even if you think it's more complicated than you think. And you can never talk about a single dimension. Here are some more of the dimensions of latency. So a lot of people think, well, serverless latency is going to be due to the runtime starting up. That's almost always wrong. The runtime starts up really, really fast. What actually happens is, in a lot of cases, since functions in the cloud are stateless, they have to accumulate some state before they know enough to satisfy the request or handle the event that just came in. And that can dominate your latency, particularly if you need to do some relational database calls or something to do that. But let's go back and look at the runtime. So what are some of the things that can happen in the runtime? Well, there's the well-known phenomenon of cold start versus warm start, whether you've been running that function recently and we've got it all loaded up on iron waiting to go, or we have to actually go get it out to S3 and deploy it before you can run it. Then, of course, there is what is your runtime startup platform anyhow? Is it a VM? Is it an interpreter? Is it a compiled program? That has a huge difference. And of course, there is the P50 versus P90 issue. So whenever you're thinking about latency, and first of all, and deciding whether it's a problem and what you can do to address this problem, you have to keep all of these things in your mind. So let's assume that we want to use serverless, and we don't like latency, so what are we going to do to address these problems? Well, first of all, we can address the cold startup problem in the case of compute, by keeping your Lambda functions warm. This is a well-known trick. Go read up on it in Google. I'm not going to say much. There's techniques for doing it. They work. It makes me grumpy. I don't think customers should have to do this, and I think we should find a way to make it so customers don't have to do this, and well, let's see what happens next year. What's more interesting is, let's talk about programming languages. We're all geeks here. We like talking about programming languages. So I don't want to diss Java, because we use it all the time. You folks use it all the time. The tooling is pretty generally excellent in terms of IDEs and debuggers and compilers and libraries for everything. And all these years later, it's still a pretty okay programming language. And it is very, very difficult to find anything that actually runs faster than Java. Runs faster, I say, once it's got itself going. The Java community, over the decades, has gotten into a habit of consciously choosing to buy runtime performance at the expense of startup performance. And You think, well, that's just the JVM, and it isn't. The JVM actually can start up pretty quick. Most often, the problem isn't Java. The problem is us. We've loaded up all sorts of startup goo into our programs, and these huge dependency injection frameworks that make thousands of reflection API calls before you can handle your first request. I don't want to name names like, for example, Spring Boot, but if you're doing that, then that's the kind of pain you can expect to have. Now, if you need to do dependency injection, you can look at something like Dagger, which is something from Google and Square, which tries to do dependency injection at compile time. But I think the real underlying point I'm trying to make is that you might be able to make Java run fast at startup, but you're not going to get that for free. You're going to have to do a bunch of extra work to do that. So maybe just don't use Java. I know that's sort of a shocking thing to say, but bear it in mind. So I have also on this slide 3 runtimes that have substantially good startup performance, by which pretty good even when cold. And they are not, however, created equal. I, generally speaking, do not encourage people to do serious server-side software engineering in Node.js. A bunch of reasons. One is that JavaScript just isn't a very good programming language at the end of the day. Things are getting better, and TypeScript is nice, but if you want a nice, modern, strongly typed programming language, why don't you just use a real one instead of something that's layered on top of something else? But my real problem is NPM. And I just cannot imagine foisting a service based on NPM on my customers because it's just uncontrollable, ununderstandable, unspecifiable, unpredictable. I'm just not going to use it. Which leaves Python and Go. So specifically, if you are a person who's in the world of scientific computing or data science or ML or something like that, you're already living in a wall-to-wall Python world anyhow, so don't fight it. Go ahead. Python is an excellent choice for serverless. It's a pretty good programming language, good tooling, good libraries, that kind of thing. And that leaves Go. And I try to be neutral about these things, but I can't. I'm just really a big fan these days. And in particular, if you're doing serverless, the Lambda runtime for Go is just freaking excellent. It is really good. There's a lot of things to like about Go. It's got good tooling, good debuggers, good IDEs, good compilers. It's so great to sit on my Mac and say, build my Go program and only build it for Linux, and I can just run it on the Lambda right there. That's just cool. Another thing is that it's often the case that we want to write highly concurrent code to get the most out of our computers. And concurrency in Go is just immensely, insanely better than Java in particular and most other languages. It's way easier to write concurrent code without getting into yourself into race conditions and deadlocks and so on. And then finally, and maybe this is an old guy talking, but I think that of all the many computer languages I've worked in over the years, Go has readability that is second to none, and I think maybe better than any. And readability is just super important. I spend way more time reading code than I spend writing code, and I think we all do. And if we're going to work effectively as a group, we have to be able to minimize the work it takes to understand what each other are doing, and Go does that. So I'm down with doing Go. That picture I showed you a few slides back of the inside of the Amazon MQ service, though the control plane there is a bunch of lambdas written in Java. And I think if we were going to do it again, we did that in like early 2017, and I think if we were going to do that again now, I would be leaning on that team to use Go, and I don't think I'd get any resistance. Let me just highlight this one blog entry that crossed my radar recently that just made a big impression on me. So these guys were a startup. I actually have to admit I have no idea what they do, but they have this application that's purely serverless. And it was starting to cost them a whole lot of money. And the reason was that the way it worked was they had this little function that they used to run for every customer, for every region, at a regular interval, quite often. And they were doing well. They had more and more customers. And so they were running this thing thousands and thousands and thousands of times at a regular interval. And their Lambda bills were starting to get really pretty high. But then they looked at it and they realized what the function did wasn't very much. All it did was pull some information in over the network and persist it into a database. And so what they did was they rebuilt it all into a single Go function that that for each combination of customer and region, just fired off a Go routine and tossed it into this, the thread pool and said, do that. And because the Go runtime is totally built to do that, it just worked. And here's the thing. Because this function was totally I/O bound, I was mostly just sitting there waiting for bytes to trickle in over the network, the runtime of this massive combo function that worked for all the customers and all the regions was actually not much longer than the underlying runtime of the individual functions that they were running before. And the reduction in their Lambda spend was just absolutely colossal. So just a success story that you might want to pay attention to. So that leaves what I think is the elephant in the room, the main thing that makes doing serverless hard in terms of latency, and that is what I called state hydration. You need to get enough state to figure out what to do before you can do it. Except for, sometimes you don't. This is an app I highlighted last year at this conference by Thomson Reuters. So what they do is they're a news organization. They get lots of video. The video comes in, it lands in an S3 bucket. So they need to be able to transcode it into lots of different resolutions and sizes and encodings so they can deliver it to all their customers. And this is pretty hard, actually, because it turns out the amount of time it takes to transcode is linear in the size of the length of the video. And it's linear with a multiplier of 1. So like a 30-minute video can take 30 minutes to transcode. And so what they did was insanely clever. They took the video and using FFmpeg, broke it into like half-second chunks, breaking it on the keyframes, which gave them a large number of very small video files that they hurled as objects into an S3 bucket and had it wired up so the arrival of each object launched a Lambda function, which then did the transcoding on half a second of video, which takes about half a second, and then it glued it all together once it was done. It was a brilliant piece of work, and the result was that the time to encode a half-hour video went from like half hour to a handful of seconds. On top of which, there was no state hydration. All the Lambda needed to know was the name of the S3 bucket, or an S3 object, and it could go and just start streaming it in and working at it. On top of which, doing capacity management for this, if you were doing a traditional server full service, would have been a nightmare. It's news. You can't predict when it's going to come in. And when something hot's going on in the world, it's coming in fast and all the time, and most of the time, nothing's coming in at all. If they'd had to scale up a fleet to meet their peak load, it would have been like a really expensive and difficult process. So, I mean, this is the kind of thing, no state hydration, unpredictable loads, divisible work where it's got letters of fire 500 meters high on the top of it saying, do this in serverless. Any other way of doing it is just wrong. But, this is a bit of a lucky situation. But, let's consider the situation where you really do need to gather some state. So I was talking to a startup, who are friends of mine, and they're super happy AWS users. And they are a tool for coordinating political outreach and political campaigns. So for the Americans in the room, that flurry of SMSs and emails and appeals to you to sign petitions and send faxes and all that stuff that was going on all year in connection with your elections, they're probably responsible for a lot of that. Now, their load is just really peaky because, well, politics, obviously. And while they were successful, their AWS bills were getting up a bit. And they were talking to me about how they could reduce that. And it was irritating because, as I said, it's so peaky half the time, more than half the time, their servers are sitting there doing nothing. So I said, well, serverless. And they said, nah. And I said, well, why not? And they said, well, Drupal. So it turns out that they are using the Drupal web framework, a reasonably popular and really not bad PHP-based web framework, to do all their stuff. And the problem is, it turns out that to do anything in Drupal, it really needs to load a lot of state. Specifically, it needs to make like some immense number of Postgres calls, like 8 or something like that, before it can do anything. So they were just not a good candidate for serverless. And then the business guy in the room said, so my team's been talking about maybe rewriting some parts of the app because PHP is starting to get in our way. And you're saying that if we rewrote it, when we do that, if we think hard about how we get ready to answer queries, we might be able to go serverless and save buckets of money. And I said, yeah. And he said to them, well, you guys should think about that. And so, guys, think about that. When you're designing software, think about figuring out a way so that you can start in a stateless way and still get useful work done. Now, you still have to retrieve stuff sometimes, but it is not necessarily written in the stars that you have to do it from a DBMS. There are a lot of different ways to recover state. For example, you might want to look at AppSync, which uses GraphQL, which is specifically designed to take a whole bunch of chatty little RESTful API calls and in one round trip give you a nicely managed package of more or less exactly what it is you need to move forward. Look at Elasticache. My laptop has a sticker on it that says, Elasticache, microseconds are the new milliseconds. Now, Elasticache is not exactly serverless, but let's not let the perfect be the enemy of the good. You can go and set up a special API specifically designed to hydrate yourself. You can recover state from a queue or a stream or something like that. There are a lot of ways to minimize the effort of state hydration by thinking about it first. And I want to illustrate this once again by example once again, ripping off the covers of an AWS service. And the service I'm going to look at is Step Function Simple Workflow, which share a common back end. And if you look at a workflow service, it's mostly just an event processor. You have millions of workflows running. I speak literally. There are millions of workflows running. And they're sending you a stream of events saying, oh, this state succeeded, this state failed, this timer went off, this new workflow run was requested, yada, yada, yada. And what it has to do is take all those requests, look at the current state of the workflow execution, and figure out what to do next. And so the designers of this service, which is a few years ago now, decided that to achieve acceptable latency, they would lock each workflow execution to a particular host in the fleet. Because that way, when the event comes in, you would send it to that host, and the current state of the workflow would be there in memory, and thus they could look quickly, decide quickly, dispatch quickly, and move along. So can you see the flaw in this scheme? The flaw in this scheme is that it might crash. Or actually, what's more likely, we might bounce it to patch the operating system or rev the software or something like that. And if you do that, you will have lost the state of the workflow. And in a workflow execution engine, the one thing you must never, ever, ever, ever do is lose the state of a workflow execution. So what they did to deal with this is they have a journal-like thing running into DynamoDB. And whenever, so we route the events to the right hosts, and the host says into the journal, oh, I got this event. And then it says to the journal, oh, I looked at the workflow, and oh, I decided to do X for some value of X, and then it goes away. And so then, if that host goes away, when the next event comes, and oops, that host isn't there, we have to route it to a new host, it can go and play the journal forward and recover the state, and then subsequently decide what to do with that workflow. Does this work? Yeah, works fine. The state-to-transition rate is perfectly acceptable. Is it simple? Oh, no, not at all. It is hideously complex. The task of making everything routed to the right place and making sure you write the journal in exactly the right way so that you never lose anything, and the task of playing back the journal and reconstructing state and trying to do it quickly when a new event comes in and you've lost the state. These are all very complicated things. And as a result, this team has, they're not all that happy with their feature development velocity because they have this insanely complex setup. And I'm pretty sure that if we were going to build this again today, we would just simply abandon that notion. We would spray the events randomly across the fleet, maybe even not have a fleet, just do it serverlessly, and make it really fast and efficient to recover the workflow state from persistent storage. After all, this is not a complex SQL query. This is, find me the current state of workflow UUID, and it's a pure key value pair retrieval, and we're pretty good at optimizing those kind of things. So here we see a design error caused by people obsessing about latency. You see the same thing in RESTful applications, where for large RESTful applications, you'll have session affinity, and they'll make a big deal about trying to route queries from a session back to the same host. That works okay. Lots of people do it. Is it simple? No, it's not at all. Does it add extra work? Yes, it does. Does it add complexity? Yes, it does. And so what I'm saying is sometimes the cure for the disease of latency can be worse than the disease itself. And so I would recommend that as you design new services, don't try do session affinity. Just route stuff around, deal with it in an efficient way, and it'll buy you lots of good stuff. I think that's all I'm going to say about serverlessness and reducing latency. And the message is, use serverless where you can. Sometimes you can't, but when you can, you're almost certainly going to come out ahead. And if you look at it and you say, oh, well, that might cause me a latency problem, don't say, OK, no serverless. Say, well, is there a way I could design around that? Because oftentimes there is. I think I'm going to stop talking about serverlessness. I'm more than halfway through this. Let's talk about something else. Let's talk about databases. So I'm an old guy, and I can remember for many years there was a period where if you were a serious developer building serious software, you had to develop it in Java, and you had to talk to a relational database because that's what serious people did. Fortunately, those days, the Java nuclear winter, as we called it, are now over. And no matter how serious you are, NoSQL databases are perfectly acceptable for modern use, and they're highly relevant in a lot of applications. We use them all the time. In many cases, their semantics, they tend to be document rather than row-based, and they tend to be optimized towards key value lookup, and they tend to be really good if eventual consistency is your thing. There's a lot of cases where they work just fine. And they can often have dramatically better performance, too, assuming you use them right. So they're a good option. I've got Dynamo up here because I work for AWS, but lots of people are getting excellent results with Cassandra and Mongo and Couchbase. And I just discovered like 5 more databases walking around the expo floor that I'd never heard of. So NoSQL is a good thing. But sometimes you have transactions, don't you? Some applications are just naturally transactional. Sometimes the data I'm dealing with is somebody's bank account or a conversational state or something like that, and you just need to be transactional. Now, I noticed that we announced transactions for DynamoDB at reInvent, but we don't have much experience with that yet. So maybe the Inside AWS talk next year will talk about using transactions in DynamoDB. So conventionally right now, the way you get transactional behavior is using a relational database. And so the question we ask ourselves is, inside AWS, building applications, should we use relational databases? And if you went to Werner's keynote this morning, you probably know the answer to this, which is we just don't do that. And there's a bunch of reasons beyond what Werner said. So to start with, relational databases, we think, slow software development down because so often a huge proportion of the semantics of your application migrates into the relational schema, and then the relational schema goes around and touches every little piece of code you have, and if you even touch it in the slightest way, you have to do a whole bunch of extra work. Second thing is the relationship between what you ask a relational database to do and the amount of work it does seems to be highly nonlinear. I mean, you can make simple queries that will cause a huge database cluster to just melt down. And it's because SQL is such a huge, vast API against a huge, vast data surface. So we just don't like that. We like relatively deterministic behavior. Another thing is that the availability story for relational databases is based on failover. If you've done a lot of failovers, you can know they can easily take minutes. And in the best case, still take seconds. And our services just can't go off the air for seconds, let alone minutes. And then the final problem is that if you are running a serious relational database, you are expected to have a cadre of DBAs. You can tell them by the long robes with silver sparkles and tall pointy hats. Sorry, there's lots of great DBAs out there. But that just doesn't feel very modern to me. That I should have to maintain a team of people working full-time just to keep my database running well. So we just basically don't use relational databases, but we still do need transactions. So what do we use? For at least 4 years, which is how long I've been at AWS, we've been using QLDB. Now, it's not exactly the same bits that we announced as a service yesterday, but it's the same technology. And right now, today, you can't launch an EC2 instance or send a message on Kinesis or scale an auto-scaling group without using QLDB technology. This is old, solid, reliable stuff. Before I talk about it, I need to give a tip of the hat to this blog entry from this guy at LinkedIn back in 2013, Jay Krebs, which is, I think, one of the most influential pieces of technical writing in recent years, which said that an append-only immutable log-based store is really the right thing to use for modern distributed high transaction rate applications. And the immediate result of that was Kafka, which is a nice popular thing. Oh, and now we're doing managed Kafka too. They announced that this morning. And that was good. Kafka's a fine thing. But it led, we were already working in that direction, and QLDB is one of those. So the thing about QLDB is at the center of QLDB is this big journal, and the transactions are at the front end of the journal where things go into it. So you do your transactions in an SQL-ish thing, and as a result, everything that's on the journal is a transactionally consistent, chronologically consistent record of all the changes that have been made to your data store. And then we read off the journal and build a summary, which you can use as a database and query. It's a really nice architecture. What are some of the key points about it that I haven't already said? The summary summary is a database, but the journal is actually one of the tables in the database, which is a really nice thing. So you can query the current state of any given record, or you can, with equal facility, query the events that got it to be that way, which turns out to be insanely useful in a lot of applications. The data are documents. I don't know if you've ever noticed Ion. We shipped it a couple of years ago. It's a JSON superset with a few extra numeric and timestamp data types. And of course, it's cryptographically chained, which provides a lot of the semantics that the people who are blockchain boosters like to talk about, but it is not a distributed consensus thing. So it's not a blockchain in the slightest. It's just a database. And most important of all, it's serverless. You tell it what your tables are, and you just start dumping data into them and querying them, and we take care of scaling it out. It's a really nice piece of technology. Let me go back to that picture of the back end of the workflow service and talk about that. So I told you we do the consistency by writing a journal into Dynamo. Well, Dynamo is a fine database, but it's not particularly friendly to journals. And we were getting one of the highest IOPS allocations of any Dynamo database in the world to support this. So we are actually, as we speak, rewriting that to use QLDB's journal and database for the purpose of that. We don't have hard numbers yet, but I expect us to get absolutely dramatic, qualitatively huge improvements in cost and performance by doing that, and also spend a whole lot less money. So that's going to be a win. So am I telling you that you should all drop everything and run out and start using QLDB for everything? Well, you can't, because I think it's still in preview. But even if you could, no. But I think that any of you who have distributed high transaction rate applications that need something journal flavored or need transactions should go and take a good serious look at this. It is a fine piece of technology. I sleep pretty soundly at night when the services that I take care of use it, which I don't when they're using relational databases often. Okay, what else was I going to talk about? Containers. Oh, that's right. I was going to talk about containers. I'd finished databases. So let's talk about containers. A lot of you people are using containers. A lot of our people are using containers, too. Here are some applications that actually have containers inside. I actually don't think we have very much to teach you about containers. Near as I can tell, the way that we use them is more or less exactly the same way that you use them as well. I mean, developers like the aspect of a container that you can, with code, deterministically and repeatably build an artifact with all its dependencies in the right places that will execute on a given platform, and that you can copy it around to deploy it and things like that. So a lot of these people are actually not only building but deploying containers. They are almost entirely using ECS to do that. They are starting to see Fargate, and I think we will see more and more Fargate because it's serverless, and that buys you all that stuff. We are not, as far as I know, using Kubernetes at all, although Amazon's a huge place, and I'm sure if you poked around, you could find some. We don't need it because we have auto-scaling and a lot of other things that do the useful things that Kubernetes does. And also because we try and do serverless wherever possible, and if you do serverless, that removes the need for that. Having said that, Kubernetes is just fine. We've got EKS. We have a lot of customers starting to use Kubernetes to manage deployments on EC2. There's nothing wrong with that. I have a feeling that there may be a vulnerability there. I think Kubernetes, well, I believe that easy things should be easy and difficult things should be possible. And Kubernetes fails the first half of that pretty badly. The learning curve is brutal. And I have this feeling in my gut that there might be something out there that only does maybe 20% of what Kubernetes does, but is 80% easier to use, and it does the right 20%. I don't know. Haven't seen it. It's just that I think people are working too hard doing basic things in Kubernetes. Anyhow, containers. Yeah, they're great. There is a discussion to be had about how serverless and containers interact with each other. And Ben Kehoe, who's a well-known loudmouth and friend of ours, Ben, are you here? Don't see him. Has asserted frequently that containers and serverless should be orthogonal. And I like that, but at the moment we have a situation that I've illustrated with this picture here, that if you want to have tens of thousands of TPS and you want to have response times in milliseconds, pretty well functions are what you got, right? You're going to end up using Lambda because it's the only thing that can provide those kind of constraints. Because as everybody knows, containers are slower to start up than functions, and VMs are still slower still. Oops, they're not anymore. As a firecracker, they can boot from bits on storage to a fully running VM in like 125 milliseconds or some shocking number like that. So you could conceivably think about responding to an HTTP request by spinning up a VM to take care of it. I'm not sure I think that's a good idea, but it's a thing you could think about doing, and we can start these things at thousands per minute. So what am I really driving at? No, I'm not suggesting you should all go out and start responding to HTTP requests by spinning up VMs. But if we could do the same thing with containers so that they could have that same kind of latency and flexibility, then, and I think we should be able to. I mean, Docker just wasn't designed with the notion that it should do a fast start, but you could have a container like Docker that maybe was. I mean, many Docker images tend to have a huge chunk of the Linux userland come along with them, but maybe they don't have to. And I envision a future in which you can get roughly the same kind of concurrency and latency characteristics out of VMs and containers and functions, and that's going to really change the world, because right now, people tend to choose between these things based on how fast they want to be, as opposed to the underlying technical characteristics. And so maybe in the future, we're going to be able to pick which way we want to deploy our compute simply based on which one of these worlds it fits into better, as opposed to how fast we need things to start. So I'm looking forward to that, and I think that's going to be great, great fun. OK, what else was I going to talk about? I think I'm done with containers. Oh, yes, integration. OK, so I don't know about you, but I never get to build software that stands alone, this proud silver tower in the middle of an empty plane. Every piece of software I write has to integrate with stuff. And when I talk to customers, people who are moving into the cloud, they're doing some lift and shift, they're doing some new cloud native, they're doing all sorts of different things, usually all of those things at once. And integration problems are at the center of everything. And in particular, one of the things that I know I hear from customers who are going to modern cloud-native stuff is saying, yeah, but I still got to talk to the accounts payable system. I still got to talk to this old thing. I got to talk to COBOL running on a mainframe. Don't laugh. There's going to be COBOL running on mainframes when we're all in our graves. And how do you do that? So integration is something that we all ought to be thinking about a lot and figuring out how to do it. So I'm going to claim that in 2018, there are three rough baskets here that integration problems fall into. I'm not going to waste your time explaining to you what APIs are. Everybody knows what they are. We're all pretty comfortable with them. I mean, it's a pretty broad brush term. An API can be anything from a Linux system call to some huge described RESTful thing that returns 600K of output, 18 seconds later. But they do have a common thread, which is APIs are generally associated with tight coupling. I call an API, and well, I stop. And wait for the API to come back and tell me what I wanted to know or do what I wanted done. Now, OK, that's not always the case. Sometimes you have APIs that are fire and forget, and you poll to see what's happened or things like that. And there's callbacks and so on. But APIs do represent, I would think, in the general case, fairly tight coupling. And that can get you into a world of hurt, particularly in a distributed serverless application. If I have serverless microservice A calling microservice B, and we get a load surge such that the requests are hitting A 5% faster than B can handle them, you can get yourself into a world of hurt very, very quickly. And that is a consequence of synchronous coupling via APIs. So let's look at some of the alternatives. So I'm going to talk about two alternative patterns of coupling, the first being orchestration. Now, to some extent here, I am talking my book. I'm have my hands on step functions. I have code in it. I'm probably the chief designer of the States language. So I'm biased on this one. But I think I have facts on my side. If you look around Amazon.com, between step functions and simple workflow and some earlier workflow engines, we are running literally tens of billions of workflows a week just to do business and be Amazon. Because the fact of the matter is that in the stuff we build, there's a certain amount of stuff that A, has multiple steps, and B, the steps fail sometimes, and C, the steps take unpredictable amounts of time, and D, need to be handled as a unitary thing, so the logging goes in one place and you can manage them as a unit. And for those, a workflow is exactly the right kind of tool that you need to get the job done. And if you're running big, sophisticated applications and you're not using workflows, you're probably using something you pieced yourself together using SQS queues and messages and so on. And that stuff is a pain in the butt, and it gets more and more complex and less manageable as time goes on. So I do strongly counsel people to look closely at workflow technology. And then finally, event-driven computing and event-driven integration. So, spoiler, let me give away the punchline. This is a big deal, a really big deal, and it's becoming a bigger deal faster. Event-driven computing, by the way, also, this is my future. I plan to spend most of the next year working on event-driven computing stuff. So we already have a lot of event-driven stuff at AWS. Those 3 services I have there, between them, they can take events from literally dozens and dozens of different sources and filter them and run them through Lambdas and deliver them to dozens of different destinations, mostly without you having to write any code, except for the code in the Lambda function, perhaps, with a lot of reliability and performance and security and so on. But there's still a lot of ways it could be better. So we're already doing a whole lot of event-driven computing. So event-driven computing is, by definition, loosely coupled. And almost, and by default, scalable. You know, when you emit an event, you don't have a tight contract. Whoever's going to receive that event can do whatever they want with it, and it's not your problem. And in fact, when I say whoever, it can be multiple parties. Once you've broadcast an event, multiple different parties can start to use it and do things with it. And once you've got your reality exposed as an event stream, you can use filtering technology, you can use routing technology, you can use streaming technology, you can talk to Firehose and dump things in, into Redshift and get analytics, you can do analytics on the way through. There's just a whole lot of stuff you can do. So let me make this into a really concrete example. Suppose you are the luckless developer who has been told, OK, for this app to work, you have to go pull change records out of the existing accounts payable system running in COBOL on the mainframe. So sucks to be you, but OK, you got to do this. So you're going to go and find out how to call this API and assemble the authentication credentials so you can actually make that call and get the information out of the old system. So what I'm going to advise is that when you do that, don't just return the value to the caller. Take that value and drop it on an event bus somewhere. Because you had to do a lot of work to get that. So why just make it available to one application? So once you've done that, any subsequent application that cares about those changes merely has to subscribe to that event bus, and it can start doing that. You've just done a favor for your future self. And we have lots of event bus products. There's SNS, there's CloudWatch events. A lot of people don't know that much about CloudWatch events, although it's a hugely successful service. It turns out that you can inject your own events into CloudWatch events, just ad hoc events. It's really cheap, and you can route them from account to account and region to region and service to service and do all sorts of nice stuff with them without writing any code at all. So I'm going to close, because I'm down to 5 minutes here, with an example from another service. So one of the things Werner announced this morning was Step Functions now has connectors. So up till today, Step Functions was able to knew how to talk to Lambdas, knew how to run Lambda functions, and it knew how to deal with polling activity workers. Well, as of this morning, Step Functions can talk to I don't know the list, ECS, Dynamo, SQS, Batch, Glue, SageMaker, a bunch of things like that. S3. So you just have, the way you do that, for those of you who know step functions, is where you would put the ARN that addresses the Lambda function. You simply put a magic ARN that says, dump this thing into Dynamo, and it just does it for you. So that's great. Now, the other cool thing it does is it lets you do something like run, for example, a Glue job. Now, Glue does not have a synchronous API. There's no way to say, run this and wait for it. It just has a fire and forget API. So the way that works is Step Functions starts that job, and then forgets about it, but it's polling this queue here. And what happens is Batch thunders away, or Glue thunders away, and does all its stuff. And when it's finished, it emits a CloudWatch event, whether it succeeded or failed. And we've written a rule into the customer's account to catch that CloudWatch event and drop it back on the SQS queue that we're polling. So the Step Functions finds out when it's all done. And the effect is, from the point of view of the person doing the workflow, that we've made an asynchronous service look like synchronous. You can say, take the data, run it through a Glue, then do something else. And to do that, we have issued no synchronous API calls. We have done it in an event-based way, a rule-based way, no coding involved, just a CloudWatch event rule and an SQS queue. This is, I think, a substantial flavor of what the future looks like. Event-based, asynchronous, serverless, scalable, robust, fast, secure, and very, very safe. Okay, now I have pretty well used all my time, so I'm not going to take questions from the stage, but I will be happy to stroll out in the hallway, wherever that is, that way or that way, and talk to anybody who wants to talk about this stuff some more. So thank you for coming out, and we'll see you all next year.